Before we move on to the next section of Chapter 13, we're going to go back to Section 13.2 and talk about inertial reference frames. So if you want to apply Newton's second law, you need to do it in an inertial reference frame. And they say here that an inertial reference frame is either fixed or translates with a constant velocity. And it has to be fixed relative to another inertial reference frame or translating with a constant velocity relative to another inertial reference frame. And although the Earth, I think they say this somewhere here, okay, so the Earth both rotates about its own axis and it revolves around the Sun, but the accelerations created by these rotations are relatively small, so they can be neglected for most applications. So we can treat the Earth as an inertial reference frame. Therefore, anything which is moving at a constant velocity or a velocity of 0 relative to the surface of the Earth is also an inertial reference frame. So if you have a train and it's traveling down a straight track, so not turning any corners, but traveling straight with a constant velocity, this is an inertial reference frame. So any experiment that you wanted to do in the train, as long as it's traveling at a constant speed, it would behave the same way as if you did it on the ground and wasn't accelerating at all. So if you wanted to play a game of pool inside the train, as long as it's moving at a constant speed, and it would have to be a very smooth track so the train wasn't vibrating a lot as it goes down the track, then there'd be no difference than playing a game of pool on a table that was on the ground, not moving. However, if your train starts speeding up or slowing down, or if it goes around a corner, this is not an inertial reference frame. So if you had the balls on the pool table and the train started to speed up, all the balls would roll to the other side of the pool table, this way, if the train's accelerating that way. And so you have to, when you're going to use Newton's second law, make sure you are using an inertial reference frame. Okay, so if your reference frame's moving at a constant velocity relative to the surface of the Earth, then you're good. Another thing which would not be an inertial reference frame is if you're driving your car down the road, and if you have something on the car seat next to you, and there's not a lot of friction between that object on the car seat, and you turn the corner, or if you stop suddenly, that object would either fly forward if you stop suddenly or go off to the side when you turn a corner. So if you tried to apply Newton's second law, you'd look at that object, and if the car is your inertial reference frame, you would say there are no forces causing that object to suddenly fly off the seat, and yet it is sliding off the seat. So you'd want to use the surface of the Earth as your reference frame to analyze that situation using Newton's second law. If you were looking at rockets or satellites, you can use an inertial reference frame which is fixed to the stars to analyze that motion. Okay, so you can either, if you're on the surface of the Earth, use the surface of the Earth as your reference frame, or any other reference frame which is moving at a constant velocity relative to the surface of the Earth. And if you're looking at a rocket in outer space, you can just fix your inertial reference frame to the stars. Okay, then in quiz 2, we looked at a helicopter which was accelerating downward with an acceleration of little g, and if a ball was also falling downward with the same acceleration, then the relative acceleration between those two was 0. So in this case, we're going to consider not a helicopter, but an elevator, and unfortunately, the cable is broke, and the elevator is accelerating downward with an acceleration of little g, and when it hits the ground, this poor person inside the elevator is probably going to die. But before they hit the ground, they have a chance to perform some fun physics experiments. So If this person has a ball in their hand and they reach out and they let go of the ball, and it's like, let's say, a meter away from the floor, if you, standing on the earth, look at this ball and draw a free body diagram, you say you have a force of gravity acting downwards, so the acceleration of the ball should be little g and pointing downwards, which is the same as the acceleration of the elevator. So because the elevator and the ball are moving downwards with the same acceleration, the ball is not going, and the ball is at rest relative to the elevator, so they're moving at any point in time, they have the same speed. The ball is never going to get any closer to the floor of the elevator, so it will always stay a meter away from the floor. So to the person inside the elevator, it looks like there's no force of gravity acting on the ball because the ball isn't moving relative to the elevator. So you, in an inertial reference frame, can correctly analyze the situation by saying there's a force of gravity acting on the ball, therefore it's accelerating downward with the same acceleration as the elevator, whereas the person in the elevator, if they try and use the elevator as an inertial reference frame, would say, it looks like there's no forces acting on the ball because it's not accelerating, or I know there's a force of gravity acting on the ball and yet it's not moving relative to the elevator, so it appears that Newton's second law is broken. Or if there are no windows in the elevator, so the person inside the elevator didn't actually know that they were in free fall and about to meet their death, well, the person inside the elevator wouldn't really feel like there was a force of gravity acting on him, and the ball wouldn't be moving any closer to the floor. It would seem to the person like in the elevator like he was in outer space.